All right, we're going to do some more graphing of rational functions. Well, finding the equation, the graph is already written for us right here, and there's so much information in that graph, we're just going to start plopping these points into our fraction right here. So I have a fraction, and there's going to be factors related to the x-intercepts. I like doing those first. So here's an x-intercept right there. Oh, and we'll do these one at a time. This guy's even. See that bounce right there? So when you have a bouncing x-intercept, that causes an even multiplicity, or in other words, an even exponent. So it's located at -1. That means this is going to be x plus 1, and it's going to be squared. Now the next x-intercept right here is odd because it crosses the x-axis. It doesn't bounce off of it. So that x-intercept is going to be, let's see, that's x minus 2. And that is a single exponent. You don't have to write the 1 for the exponent. I'm just doing that to be clear. Now I have a vertical asymptote going straight up the graph right here. And that guy is going to be a factor on the bottom of my equation. And it looks like that's x minus 1. But before we move on to the next part, let's take a little closer look at that vertical asymptote. Do you notice how the function is tracking it up and up, like up on both sides of the vertical asymptote? That right there is even vertical asymptote behavior. So that means our factor is going to be squared. Okay, there is one pesky little hole playing around here, right there. So that is going to be located in our fraction on the top and bottom. And that's going to be, let's see, x plus 3 on the top and x plus 3 on the bottom. Now, I'm all ready to talk about this vertical scaling factor that we've found before. But I just want to do a little sanity check. Does this equation look right? How many x's are there on top? 3. How many x's are there on bottom? 2. Excuse me, 1, 2, 3. I got that wrong. There's 4 on top. So there's x to the 4th on top, and there's x to the 3rd on bottom. That right there is top heavy. Now, is that okay? You have to be sure that you're doing something okay before we keep going forward. And I think that's fine, because take a look at what we have here. Big old oblique asymptote going sort of slanty-wise, which means you have to have an equation that's top-heavy. Ours is, so this all makes sense to me. So let's now plug in a non-zero y value. And, oh yeah, there's one right there. See this one right there? I'm going to use that. It's 0, positive 4 for the y. So y is 4. All the x's become 0. 0 plus 1 squared. And 0 minus 2. And 0 plus 3. On bottom we have 0 minus 1 squared. And 0 plus 3. Well, the 0 plus 3's cancel out. That's easy. Which leaves us with 4 equals -2a on top and 1 on bottom. Okay, so this is going to simplify pretty fast, and we get -2 equals a, which means f of x equals -2 times x plus 1 squared. That's from the x-intercept. X minus 2, that's another x-intercept, but not the bouncing one. X plus 3, that's from the hole. We'll just fill in the hole right there. And there's one more vertical asymptote. X minus 1 squared. Okay, that's the equation. And before you go, I want to tell you about a shortcut. This is really cool when it happens. Do you notice this -2 right here? Well, that happens to match up exactly with the slope of this oblique asymptote. Okay, that right there is the slope. Now this only works. This only works when you have an oblique asymptote. You can't do this trick when you've got a horizontal asymptote, especially not at y equals 0. But this is a shortcut that exists when you have an oblique asymptote or a slanted asymptote.